All right. Hello, everyone. Welcome back to our conversation about precipitation reactions. We are now going to discuss a method that we utilize that looks at the different solubilities of various salts that allows us to then separate ions from these salts or ions in solution containing these salts using their differences in their solubility. So we call this selective precipitation. So think about being selective, you're being choosy, right? So if we're talking about selective precipitation, this is the intentional precipitation of one ion from solution as a solid while leaving other ions dissolved. And we can achieve this by utilizing the differences in molar solubility of our various salts. So selective precipitation, intentional precipitation of one ion, leaving the others dissolved in solution. So for example, let's look at the following silver halide compounds. So we've got silver chloride, silver bromide, and silver iodide. I have given us here in red our KSP values for each of these salts. And remember, KSP tells us the solubility product, aka the product of our amount of moles or concentration of ions in solution raised their stoichiometric proportion in a saturated solution. So we can't use KSP as a direct means of identifying which salt is more or less soluble than the other. If we really wanted to compare solubilities, we would need to look at the molar solubility. So let's do that real quick. Let's identify what the molar solubility would be of each of these salts. So recall if I've got silver with some kind of halogen, so we do Ag on the H is hydrogen, so AgY, solid. If that were to exist at its point of saturation, there would be an equilibrium between the silver ion dissolved and the anion associated with that silver ion, meaning that the KSP is equal to the concentration of the silver ion times the concentration of the anion. And we know that because this is all a one-to-one stoichiometry, for every mole of this dissolved, we create an equimolar amount of the silver ion and the anion. So if we're talking about moles of solid dissolved, then we're talking about the molar solubility. So this can be replaced as S times S or S squared. So if we're thinking as KSP is equal to S squared here for our particular salt, then S for the silver chloride is going to be our 1.8 times 10 to the negative 10 raised to the 0.5 power, taking the square root of that. I get 1.34 times 10 to the negative 5 moles of solid dissolvable per liter. For the silver bromide, 7.7 times 10 to the negative 13 square rooted. Allows us to solve for the molar solubility of silver bromide, S, that is 5.93 with rounding times 10 to the, let's see here, no. Okay, there we go. We have a squared instead of square rooting, there we go. So 8.77 times 10 to the negative 7 moles of solid silver bromide dissolvable per liter And then silver iodide, that has a KSP of 1.5 times 10 to the negative 16. So if we were to square that, we get a molar solubility for that salt of 1.22 times 10 to the negative 8 moles of solid dissolvable per liter. So we do in fact see here a correlation between KSP and the actual solubility of our substance. But just a quick reminder that like KSP is not equal to the solubility. So we obtain, oh gosh, obtain the solubility S from KSP. They are not equal to one another. So let's talk about this idea of selective precipitation. So being choosy about what we precipitate. So let's suppose that we had a beaker that was a solution containing a mixture of the 3 different halide ions. So we have iodide, chloride, and bromide ions in solution. And we are going to ask ourselves what would happen if I were to add silver ions slowly, so in small quantities, bit by bit, into this beaker. So because I'm adding silver, and I see that the solubility of silver iodide is least, then by the time I add this amount of silver ion, then all of my silver iodide is going to become precipitated out. So first I would see a precipitate that is silver iodide. And then if I were to add any quantity greater than this, but less than this, I would then be approaching the point where I could hit saturation for my silver bromide compound in solution. This would then, at the concentration of 8.77 times 10 to the negative 7 molar of silver, give us a saturated solution of silver iodide and silver bromide. So we would then form our second precipitate. And then lastly, silver chloride, which is the most soluble of each. This would require an even greater concentration of silver to be added. So after we had precipitated out the silver iodide, the silver bromide, we would then see the precipitation of the silver chloride. This would be our third precipitate. And again, we are able to decide like how much of our silver we add so that we can choose which of the following we want to precipitate out. So let's say you wanted to remove bromine from your solution. If I wanted to remove bromine from the solution or bromide ion from the solution, I cannot do so without first also eliminating all of my iodide. So in this case, I would probably, like, let's say I wanted to do bromine and not iodide, I could look for a different ion that's not a silver-based ion that has a lower solubility with bromine than iodine, or vice versa. But in this case, if I wanted to get all of my bromide out, I would first have to precipitate out my AgI and then add enough so I'm sufficiently able to precipitate out the bromide. So this is the main idea behind selective precipitation. Now let's do an example of what this might look like. So for example, what concentration of potassium chromate, K2CrO4, will maximize the precipitation of either barium or strontium that exist in a solution of known equal concentrations to one another without precipitating the other? So we want to maximize the precipitation of either only barium ion or strontium ion. And this precipitation is going to happen when we add some amount of our potassium chromate. So what concentration of potassium chromate? This is what we are trying to find. This is our goal. So how much can we add to precipitate one of the two ions? And I've been given some information here. So I've been given information about barium. So specifically the precipitate that could be formed between barium and chromate. I have the KSP value for that. And then I have also been given the strontium KSP. So let's consider like kind of two cases side by side. So let's consider like how much chromate ion will begin to precipitate the barium versus how much chromate ion will precipitate out. Too many P's here. UPT. The strontium ion. So in order to do that, I need to consider what is happening at the point of precipitation. So if we're talking about precipitating, then we are talking about the scenario where we reach our saturated solution equilibrium. So let's go ahead and write out the dissociation equilibrium for each of these potential precipitates. So we've got the barium chromate solid, which when in its equilibrium with its dissociated ions means it is in a saturated solution. It has hit its max point of saturation. And I could write the same thing for our strontium chromate. Just the cation changes. But what's different is I have the KSP of my barium chromate is 3.6 times 10 to the negative 5. And for my strontium chromate, my KSP is 1.2 times 10 to the negative 10. All right. Let's look at the problem here, see if there's any other pertinent information for us. We were told the concentrations of the barium and the strontium in solution. So we know that the solution contains equal molarities of both of these cations. So that means that I know that the concentration of barium is equal to 0.30 molar, as well as the concentration of strontium. That is, there we go. That is 0.30 molar. So now let's remind ourselves about what the solubility product is. It's an equilibrium constant for the ions that are produced from a solid dissociating at its saturation point. So KSP, solubility product, is going to be a product of our ion concentrations at this equilibrium. So this is equal to concentration of barium times concentration of chromate. 1-to-1, so I don't have to worry about any exponents. So this is equal to our 0.30 molar times our concentration of chromate. Same deal over here. I could write the KSP expression for strontium chromate. So that is the concentration of strontium at saturation times the concentration of chromate at saturation. And we know the concentration of strontium in the solution. So this is going to be, again, our 0.30 molar concentration of strontium times our concentration of chromate required, or that would be present in the solution in order for us to be in our dissociation equilibrium with the precipitate or the solid strontium chromate. So this is going to be then KSP is equal to a value, and I want to solve for how much chromate. So I'm going to take my KSP and divide it by my 0.30 molar. This will leave behind the required chromium concentration. In order for us to precipitate each of the individual salts. So let's get these numbers, even though we can kind of see which one is going to have a lower amount needed to precipitate. So we've got first for barium, 3.6 times 10 to the negative 5 divided by 0.3. This gives us 1.2 times 10 to the negative 4 molar. This is the needed concentration of chromate, Cr2O4 2 minus, to precipitate barium chromate. Whereas here with the strontium, we have 1.2 times 10 to the negative 10. Divide that by 0.3. This gives us 4.0 times 10 to the negative 10 molar. So this is the amount needed of our chromate ion. To precipitate out all the strontium. Looking at which ion would precipitate out first, that is the ion that requires less of the chromate to be added, because once we add this amount of chromate, the 4.0 times 10 to the negative 10 molar concentration, to our solution containing strontium and barium, this will make us hit the saturation or solubility point of our strontium chromate solid. And so we would begin to see this precipitate out first. So because less is needed to precipitate, when we add the smaller amount, this is the amount that is needed. Which means that the strontium precipitates first, because we have to add a lesser amount of chromate in order for that to reach its saturation point. All right, we did not need this slide. Go us. We did all our work in one of those many slides. So boom. Which means that we can now talk about how, using our kind of foundational knowledge about equilibrium in general, specifically Le Chatelier's principle, we can now talk about how the solubility of a particular salt can be affected or shifted by the presence of other things in the beaker. And this is exactly what we look at when we look at our KSP silver acetate lab. So in our next video, we're going to talk about some factors in solution that could affect the solubility of a particular ionic salt. And then from there, we'll be done with ionic equilibrium and we will move into our first conversations about thermodynamics. So see you in the next video.